Hello, my name is Ryan Schumacher, and today I'll be presenting my report on polylactic acid from potato products. Go through an outline of what I'm going to talk about today. Start with the introduction to polylactic acid, or PLA as I'll refer to it from now on. Talk about polylactic acid structure and its properties. We'll talk about the fermentation profile to get there. We'll talk about the production of polylactic acid, uses for polylactic acid, its biodegradability, the opportunity cost of polylactic acid and its production, and I'll explain that more in detail, and the economic analysis of where the market is today. So, as an introduction to polylactic acid here, first it's a biodegradable thermoplastic that's made from fermented carbohydrate starches. It was initially used in the medical field. Worked good for that. It's compatible with the human body for bone grafts and different things like that, although it was very expensive to use at the time. But that's what kind of kept this thing going. It was actually first produced in 1875 by a scientist named Palouse. And Cargill commercialized it in the early 1990s, and eventually later in the 1990s merged with a joint venture with the Dow company to create a company called NatureWorks that is still one of the leading producers in the US today. And over here you can see I got a picture of an example of something made with polylactic acid. This is actually a 3D printed polylactic acid jet engine made with little filaments, so it's quite versatile. Here you've got the 2D molecule of a polylactic acid. Notice it's got two carbons, oxygen, hydrogen, and a methyl group. It's made of long chains of molecules, so that's how you get the polymer of it. The two isomers are the lactic acid, the L-lactic acid polymer, PLLA, and the D-lactic acid isomer, PDLLA, and you can get it when they're both combined. So as I talk about more how these structures go together, this will make a little bit more sense. The D-lactic acid actually has a bit more commercial viability. It has a higher molecular weight, some superior properties, and therefore better value. The structure and properties of polylactic acid are very similar to a plastic water bottle. So it crinkly, makes a lot of noise, very strong, but isn't very stretchy. Therefore it's brittle, so it breaks at less than 10% elongation, meaning that if you're strong enough to grab the water bottle and pull it apart, it would stretch 10% or less before it actually ruptures and breaks. It actually has poor gas barrier properties. So what does that mean? It's not mean that gas leaks out right away, but if it sits for days on end, there's actually some permeability there that isn't very good. It can have a high molecular weight depending on how it's made, as I mentioned earlier, and that creates a better value the higher the molecular weight of the product. And some of the things that brings to it are the melt temperature is higher, so it can be used in more applications, higher temperature applications. It had increased tensile strength, so tensile strength is the strength when you're pulling something apart before it breaks, and it has better elasticity when it's got a higher molecular weight, meaning that if you're pulling that water bottle apart, it's going to be able to stretch a little bit more before it actually snaps and breaks on you. The other nice thing about it is it has one of the more superior transparency levels compared to other biodegradable plastics. So we get in the fermentation of it. We don't ferment directly to polylactic acid. You actually start with a carbohydrate source, and it gets fermented into a lactic acid. And that's very similar to the fermentations that we've been talking about all summer here in class about lactic acid fermentations. Typical sources: corn's probably the biggest one. Potatoes are certainly an option to use. Sugarcane is popular, as is wheat and tapioca, all good common starch sources for that. And in the bottom here you can read some of the common strains that are used to do this lactic acid fermentation, which again are not too unlike the ones that we've been talking about in class. Here we've got kind of a little process flow diagram of how it works on just the fermentation side. And again, we'll go through the steps and kind of get you set up here. So you start with a substrate. You can do some pre-treatment where you might throw some extra enzymes in there to help break down the carbohydrates so you get a sugar source for the lactic acid bacteria to ferment. You go into your fermentation chamber. You're going to adjust the pH a little bit with some lime, which can increase it. You're going to add your microorganisms, just like we've been talking about. Nutrients are very common in the commercial industry. After the fermentation is done, you're going to go to a biomass removal step. So you're going to get out all the fibers, the non-fermentable sugars, all the solids that are doing you no good. From there, you're going to go through some more refinement where it gets reacidified, using gypsum to filter it and kind of refine it even more, going down even to further processing steps with the crude lactic acid. So you might be some washing steps going on there. Then you're going to concentrate it, so you're going to remove a lot of water out of it. And then lastly, you're going to purify it to get a very pure lactic acid. And the level of purification really comes into play here. The purer it is, the better your polylactic acid is going to be and the more value you're going to have. So we'll get into production of PLA now. So high quality polylactic acid starts with high quality lactic acid. And lactic acid is then synthesized into a molecule called a lactide. And a lactide is simply a ring closure of two lactic acid molecules. So if you remember back a few slides where I had the 2D structure of the molecule, you might recognize very similar structures here, but they're repeated. So if you actually take it, open, connect to, and connect them together so they actually form a ring around there. And here you've got the D-lactic acid I talked about, the L-lactic acid, and the combination D/L lactic acid molecule. Next step in the PLA production, once you have your lactic acid, you get it condensed and polymerized. So you do a pre-polymerization step where you use high heat and vacuum to polymerize it and get all the molecules start linking up. Then you're going to synthesize it here with the lactide using a catalyst, which is typically tin octanoate. And again, that's going to be at high temperature and high vacuum. And then it's going to sit in the reactor, do what it needs to do. You're going to have some of it that's actually going to recycle back around, so the things that didn't react will go back through again to keep purifying it and get better recovery rates. And then your crude lactic acid is going to come across and go through a purification step where you remove the impurities and create a pure lactide out of that. The other thing about that is when you're purifying it, there's a couple ways to do that. Distillation and crystallization are the two popular ways to do it. Distillation is cheaper, but you're going to produce a less quality product. And crystallization is more expensive, but of course, higher quality product. So we've fermented our starch source to lactic acid. We've now synthesized lactic acid and lactide, and now we're going to take that lactide and convert it to PLA, and that's done via an ionic polymerization act. And you react that in a vessel, temperature of about 140 to 180 degrees Celsius. Using a catalyst again, here it's typically tin oxide. And that actually opens that ring structure back up again, referring to a ring opening polarization or rope. And one of the nice things about that particular chemical process is it allows very tight control of the process. And hence with tight control of the process, you have good quality control. So the uses of polylactic acid. So as I said, traditionally it was used in the medical field, used for prosthetic implants, bone surgeries, wound closures, and that's really what helped it kind of keep going and keep developing, right? I mean, things in the medical field are expensive, so they can afford to put a lot of money into the development and production of this product and keep it going. Whereas if you could have used it in the medical field, it probably wouldn't have the success it has today. More of the recent uses, now that you've got large-scale commercialization and you've actually lowered the production costs, it's now in the consumer mainstream market. So this particular product here is an Activia yogurt cup made by Dannon, and this is actually being used in Germany. So if you zoom in real close, you'll see some German writing on there. So their rigid plastic packaging is used. It can be used in flexible film bags. It can be used in cold drink cups and cutlery and bottles, just like a plastic water bottle. And of course, as I showed a lot earlier, with that model jet engine and 3D printing. Now we're getting to the biodegradability of the product here. The beauty of this is a lot of things going for it from a biodegradability and sustainability standpoint. Sustainably sourced, so you're using starch sources. So I happen to work in the French fry industry, and when you make French fries, we have a byproduct, which is just a pure starch stream that comes out of the water when we're cutting potatoes. Well, we don't really have a good use for that starch a lot of times, so we can use that waste stream to now convert it into a plastic. It's biocompatible, meaning that you can use it in the medical field, implants inside the body. It's biodegradable. Now, there's a few tricks with the biodegradability here. It's best under industrial composting conditions, which are actually outside the range of a typical landfill. So industrial composting is going to be greater than 60 degrees Celsius, which is quite warm, and a relative humidity of greater than 90%. So a lot of moisture in there too, and those typically aren't things you're going to find in typical, commercial landfill requiring industrial composting. Now, although that may seem like, wow, what are you going to do with this if you can't just throw it away and recycle it? The other side of that is the good side, is you don't want it degrading when it's sitting on the store shelf just because it's got water and it's maybe a little warm in the store. So that keeps it stable as the consumer has it in their closet, or as a store has it, or they ship it in trucks. It might get a little warm. It's not going to degrade on you. But under good conditions, you can see here day 1, after a month, quite a bit of breakdown, day 38, day 58, and by day 80 you could break that into the ground and plant something if you wanted to. Now I'm going to talk about the opportunity costs of lactic acid and PLA production. So what do I mean by opportunity costs? I'm referring specifically to the opportunity cost of starch. And it's basically the revenue you've lost by making polylactic acid that you could have made using it for something else. So if we go back to, say, the potato french fry industry that I come from, we use starch as a good source for biogas in a digester. So extra starch gets washed down the drain, sent out to our wastewater system, and out to a digester where anaerobic bacteria break it down and create methane that we then pipe back into our boilers and burn it instead of natural gas, hence saving us money. It can be used as animal feed, which is much lower value. And a lot of our starch is also used and sent out to a secondary processor where they'll refine it to a high food grade to be used in, just like cornstarch as a thickener and for gravies, things like that. And then it can also be used as industrial grade starch. So the best example of that would be the paper industry. Shiny coatings on paper is actually coming from starches. And last, we'll talk about the economic analysis of the product here. So with increasing in technology, breakthroughs in that, along with processing methods and continuous improvements, they've now been able to make it commercially viable. It's actually the first sustainably produced renewable bioplastic, which is kind of interesting. And some of the prices we'll talk about. So the market price today is about $1.50 a pound, and again, that depends on, like I said, the quality of your product, but good average range. The global market back in 2015 was actually 1.15 billion pounds a year produced and consumed, creating a revenue of $2.21 billion a year, which is quite a large market for polylactic acid. Thank you for listening to my presentation today, and feel free to reach out with me with any questions.